all right.
So like, are notes absolutely necessary to?
I would take notes if you can. So, if not, have somebody else take them and then just copy them. So, all right. Let's walk through the differential quotient here today. We've been talking about trying to find slope, right? An average rate of change. So an average rate of change. In linear equations, it's really straightforward, right? The average rate of change is m. It's that delta y over delta x, which is the change in y's over change in x's. It's rise over run, however you want to say it. This is what we talked about in algebra class. Fine and dandy. If they give you equations, you can find the average rate of change pretty straightforward. If it's a linear equation, I think this is a problem like I did yesterday, something very similar to this. Okay? You don't need to do the differential quotient of that problem, because that problem is a linear function. It's a straight line. The reason why is that there's no power on this equation, so it's a straight line. And when you have it into this form that we did in the last test, what's my slope on this problem? 5. That's what the differential quotient would give you. It'll give you the slope at any moment on that line or function. So, but here's the problem. That's a line. And the reason why the differential quotient will give me 5 is because it doesn't matter where you're at on the line, the slope is always the same 5 over 1. It's the same slope the entire time because it never changed. It was just a very constant function. It was rising the whole time and running to the right. We're going to do problems that isn't the case, where you have to do the differential quotient on something that's far more complicated than that. Today we're just going to start with the basics, real easy stuff. Then we're going to work our way to the more challenging questions as we go. So the goal today is I want to do 2. I want to do 2 problems where we do the differential quotient. We talk about what it is, why do we find it, what's the whole purpose of it, and then tomorrow we'll do some more challenging questions and you'll get some homework tomorrow. The goal tomorrow to do the homework, I want to give you about 4 problems tomorrow. It'll be a worksheet, you get 4. You have to find the differential quotient and put it to use and why do we actually use it. That's what we're going to look at tomorrow. Okay? All right, does that make sense what we're doing today? The goal today is just to practice this differential quotient and make sure you know what it is. Okay, here we go.
Pineapple juice?
All right. So, all right, so differential quotient. If you don't know the formula for it, it'll be printed on every worksheet or test that you have. If when I get to this question, on your next test, this will be one of the first questions you're going to have. The differential quotient looks like this. Yeah, it's this one. This is what we're going to be doing. This is the first section. They have you practice this thing. And we're going to look at a couple different items with this, and that'll be what we're going to look at tomorrow. It is finding slope. That's all it is. It's very simply put. It's how you find slope for any type of function and average rate of change anywhere on the curve. So, for instance, let's say that my function is this. Let's say that's my function. Do we agree that that thing's a curve?
Yeah.
Okay, so the slope will change over the life of that problem. In fact, that problem kind of looks something like, let's see, it's going to look like this and -3. It's going to look something like that, and the graph will actually look something like this. Now, how I put that together. It's an even power, the tails go the same direction. My x-intercepts, if I factor that thing apart, will be 0 and -3. And so, as you look at this problem, the slope actually changes. If I'm on the left side of this graph, the slope is negative. It's going down. If I get closer and closer to this zenith point, or the max or min, the slope actually turns out to be 0. And then as I go to the right, the slope goes to positive again. Does that make sense? So the slope changes constantly over this problem. So when we do the differential quotient won't just spit out a number, because the number doesn't apply everywhere on the graph. It'll spit out a function, a formula. And the formula will tell you what your slope is at any moment on this curve. Question.
So if it's like x squared, or even if it was like 5x squared, it always has to go up and down at the same rate, right?
Yeah, just because the square means the tails go the same direction, it doesn't matter what the leading number is up front. The only thing I use the leading number up front for is to know if it's going up or down. That's really all I use it for.
Well, like, it couldn't be like that, right?
Like, what do you mean?
Couldn't be more steep on one side than the other.
No, when you do parabolas like this, the incorrect word to use, they're very symmetrical, even though I don't like using that word because it's not over the y-axis.
Yeah.
They're very balanced.
Right.
It's not going to be lopsided. It's not going to, it's not going to be very gradual and something just spike really quick. It's got to be the exact same motions the entire time, like really fluid, flowing the whole entire time. And so when you start to look at other functions and other powers, yeah, they could be off a little bit. It's just because of the powers that are involved. So that's what we're looking at in this section. So it's kind of a little bit of a continuation from the last unit we did, but we're doing different stuff, right? We're finding different items. There's a different purpose to why we do this stuff. But that's what we're going to be looking at. We can find the slope at any moment on a curve by doing the differential quotient. The goal today is to figure out how to do it. That's all I want to talk about today. I don't want to do anything else other than just review with that, because my pre-calc kids, they've been doing differential quotients. That was their last unit. You guys did it. It was the first chapter test you took. Not the pre-test. It was the first chapter 1 test that we took. You had to do it. It was a long time ago. I think Mr. Stein was here at the time. So I want to review it with you right now. So what?
So we didn't actually learn how to do it.
Well, we're gonna learn how to do it now. So all right.
He looked like a Julian.
So
He was
all right.
David, wasn't he?
No,
Okay.
I'm not gonna
So
Jason.
okay. All right. Let's walk through how to do it. So the formula I'm using, just so you know, I'm going to try to color code this, just so you can see where all my stuff is coming from. Okay, this upper left corner I'm going to put in purple, and then the upper right corner I'm going to put in orange. Okay, so that way you can kind of see where am I getting this stuff from, where is it, why am I writing it the way I'm doing it. So the upper left corner, it's the original function I give you, that one, with x plus h's plugged in. Anywhere there's an x, you're going to rewrite that problem with x plus h's plugged in. So it's going to look like this. Anywhere there's x's. So if you have a bunch of x's, you'll have a bunch of x plus h's everywhere. If there's any just normal constants, those will stay. They don't have x plus h's. Only when there's an x sitting there will it have it. So if there was like a plus 5 back here, you just have a plus 5 right here. Okay, does that make sense? We'll do one of those in the next one. Okay, we're good so far? That's just the upper left corner. Now, what do I need to put next?
The original.
The original. I have to subtract the original function. The original function, I'm going to put in parentheses, is that x squared plus 3x. You have to subtract the original function off of it. This, I always tell pre-calc kids this, but they don't believe it until they have to do it. The setup to that is always the toughest part, because I don't tell you what to do. You have to know that you take that function and apply it to this thing. Then the work after that is the easy stuff. That's the stuff that most people don't have problems with. It's just getting that written down so you know how it's set up for the first time. And what we're going to do is we're going to simplify this thing down until it's down to a simple function at the end. Then what we're going to do is we're going to just go to the next one. The reason being is that we're not going to look at the purpose of doing this until tomorrow. We'll start looking at slopes and all that good stuff. Okay? All right. Questions? I'm not done yet. That's just the setup. All right. Upper left corner. How do I do this part? What do I have to do? Foil. It is 2 parentheses back to back. You do not distribute the power of 2. You actually have to foil those 2 parentheses out. That's the part that usually gets people for the first time. So I'm going to foil that out. So this upper left corner, the h just goes in the bottom. It's going to be x squared plus xh plus xh plus h squared. That is the upper left corner up here. Now, if you want to simplify that and add the xh's together, fine. Don't need to, don't do it. Now, the middle part right here, what do we have? 3x plus 3h. 3x plus 3h. And then on the right side, what do we have? negative x squared minus 3x. All right, so there's your whole top of your differential quotient. That's kind of foiling, distributing, whatever you need to do. Now at this point, there's always a safety check to see if you're doing it right. You'll know you're doing it right if everything that doesn't have an h cancels out. That's how you know that you're doing this correctly, the first steps. So anything that does not have an h, so just like to prove my point, x squared, those are gone. One was positive, one was negative. That's perfect. They didn't have h's anyway. 3x and negative 3x, those are gone. They didn't have h's. Anything that doesn't have an h will cancel out. That's a safety check. Did I do it right? Did I set it up right? Did I foil right? All that good stuff. Now, the things that are left have x's in them. So, or h's, I should say. So this is going to end up being xh plus xh plus h squared plus 3h. And this is all divided by h. Okay? And now we want to divide everything by h. This is the law of division. And if there's anything on the bottom of your fraction, you can divide everything by it. So if I do this correctly and I divide everything by the h, what will happen is the h's will start to cancel. And I have this, okay? This is what the differential quotient gets down to, right? Because that one h is still special. What was that? Yeah, you can combine those. So you have two x's, the h, the 3, right? You can combine the two x's together. Okay. Yeah, and then that's what we're going to look at tomorrow. Like, then we look at the specific stuff that we do with this, right? We'll start plugging in zeros for h's. I'll explain that more tomorrow. We'll start to figure out what that's used for. Like, what is this function actually telling me? Like, what does it mean for slope? We're going to look at that tomorrow. The goal today is just to see how the differential quotient setup looks. Does that make sense? Okay, let's do another one, but now let's do one that's a little more challenging. Not crazy, but let's just do one a little more difficult. All right. We're not going to go further on that one today. Tomorrow we'll come back to it. So I'm going to ask that tomorrow somebody remind me this problem. We'll come back to it. We'll look at the next piece of it. Sure. Okay. So let's do one more example just to see how it works. I'm going to do something a little more challenging. So it's not super difficult. It's just I want to pick a little more challenging type of problem. So the function I want to talk about today. Okay. Let's go with 4x squared plus 10x plus 5. Now, I consider this to be a little more challenging. It looks a lot like the last problem, I know, agreed. It's only got the 5 on it. What makes this one challenging is that 4 out front. I'm not asking you to factor or anything like that. We're just going to set it up. Question.
Are these the ones that we had to do the triangle thingy?
Yes. Yes. Those are the ones we're going to look at tomorrow. The real challenging ones, yeah.
Pyramid of death.
What pyramid?
Oh, I'd love to see that.
Yeah, we'll look at those tomorrow. All right, so, okay. Let's walk through the setup on this one. Again, I just want to do the differential quotient. We're not going to do any extra steps on these. We're not going to, solve and find max or mins or anything, or slopes or anything like that. That's what we're going to look at tomorrow. We're going to look at the purpose of doing this stuff and look at the more challenging question, like Orion was saying. We're going to look at that. We're going to look at that stuff later. Now, on this one, the setup is the tough part. Wherever there's an x, you have to put an x plus h. So, for some reason, I always have some people that always get that first part wrong. They always put too many x plus h's, or they put them in the wrong spots. Wherever there's an x, you replace with x plus h. Then you have to subtract the original function off of it. The original function is the 4x squared plus 10x plus 5. And this is all divided by h. Okay, questions on the setup? Somebody wake up Happy Miller.
I'm awake.
All right. Now, what made this one challenging? It's that stupid 4. I always see a lot of people get this wrong. You do not distribute the 4 first. You have to do exponents first. It's an order of operations, parentheses, exponents, then multiply and divide last. So I have to actually have to foil this 2 parentheses out. You're just going to leave the 4 out front of it. And I know that seems tedious. It's like an extra step. But if I foil that out, And I FOIL first, outer, inner, last, and this is x plus h, right? You'll start to figure out, like, it's always the same math. Like, I've already done it. I've already FOILed out the x plus h's. So you just, if you know those answers, you can just carry them to the next problem. You don't actually have to think about it too much. You know that it's going to be this exact same x plus h's and h squares. Like, you don't even have to think about it. You just carry them from the last problem. If you know you go to bigger powers, that's when Morgan was talking about we use Pascal's triangle and do some more difficult types of problems with it. On the next part, so I've FOILed that out. I noticed I didn't do the 4 yet. What about back here with the 10?
Distribute.
Yeah, so distribute. Both items have to get a 10. The 5 stuck around. That 5 didn't do anything, didn't have any numbers on, didn't have any x plus h's. Now, in the back, what do we do back here?
Negative.
Yeah, the negative sign has to go to everything. So this can be a negative 4x squared, negative 10x, and a negative 5. If any of those were negative, they become positive then. And this is all over h. All right. Now,
Wake me up.
okay, now, so I would distribute the 4. So we get 4x squared, 4xh, 4xh, plus 4h squared. That's distributing the 4 to everything here. Now, I know that some people like to combine like terms fine. Still got to distribute the 4 to it first. Now, in the back, I still have the 10x, the 10h, the 5, the negative 4x squared, the negative 10x, and the negative 5. And this is all over h. Now, how do we know if we're doing it right?
X's cancel off.
Anything that doesn't have an h cancels. So it's not just things with x's. So I agree the x's are gone, but 4x squared, negative 4x squared. 10x, 10x, 5, and 5. Things that don't have h's, there should always be an opposite. Don't get in the habit of trying to do shortcuts too quick. Some people, like, they start to know, like, I don't even need to write the back because it's going to cancel. It's good. It's just good math to write down all the terms, cancel them later to show correct mathematics. I want to be able to follow your work step for step, and I don't want to see shortcuts happening. I'm not assigning too many of these. We'll learn shortcuts later, significant shortcuts where you don't have to do all this crazy stuff. And so that's what we need to learn the process of, like, how it was created. Like, this is the way it was created. Now, what we have here is we have 4xh.
8x.
4xh, yep. 4h squared and a 10h, and I don't think there's any h's left. It's all over h.
What are the chances of that?
And then the last step is you actually divide them. You divide everything by h, and what we're left with,
8x and 4h.
yeah, 8x plus 4h plus 10. That's, and I combine like terms, I divide everything by h. That's the 4x and 4x add together. The 4h squared, it has an h left, and the 10 left in the back.
Is that it for today?
That's it for today. Now, okay, tomorrow, we're going to look at Pascal's triangle. We have to look at what is the purpose of why we're doing this stuff. Like, what was the whole reason why this was created in the first place? Like, average rate of change, slope. We're going to look at an assignment tomorrow. It'll be probably about 4 problems where you have to do the differential quotient to it and do some extra stuff that we're going to talk about. Expect a couple easy ones. I consider these to be easier. We'll expect to see maybe a difficult one and then kind of a more challenging one after that. We have a lot of stuff to kind of recover that we haven't seen for a very, very, very long time. So that's what we're going to be looking at tomorrow. We have lots of stuff to, like, kind of narrow down. All right, that's it for today.